Welcome back to the demo on exercise 7. In this exercise, you'll reuse the simple pendulum model created in the previous chapter to add 2 more bodies and 3 more joints to create a 4-bar mechanism. In the process of creating this, you'll also investigate the redundant constraints and modify your model to remove them. You'll also use a motion function to measure the torque from a motion driving the model and also plot this. So you can either reuse your model from the previous exercise, which is recommended, or you can open a model which says chapter 7 exercise start and chapter 7 folder, and you can start building your model building process. So go here and select this. So this is where we had stopped in the previous exercise. So let's begin by renaming the points. So let's go to the model browser and expand points folder. So I want to rename point 0 as point A, 1 as point C, and 2 as point B. So now I also want to add 2 more points. So let's go to this option. I'll call it point E. So here I'll change to point E, say OK. And then 1 more point, so that's point F, say OK. So I've created points from point A to point F, which does not have point D. Okay, so now I'll be giving the coordinate values for these hard points that I've created. So for point A, the X coordinate is 921, Y coordinate is 580, and the Z coordinate is 1124. So next for point B, it is parametrically connected to point 0 or point A. So I will delete this parametricity and give specific values for its coordinates. So 918 for the X coordinate, 580 for the Y coordinate, and 1114 for the Z coordinate. Similarly for point C, it is 915, 580, 1104. For point E, the X coordinate is 878, Y coordinate is 580, and the Z coordinate is 1108. For point F, the X coordinate is 878, Y coordinate is 580, and the Z coordinate is 1118. So don't worry, the model hasn't disappeared. You just have to fit the screen. So just click on the graphical user interface and hit F key on your keyboard. This is the shortcut to fit the screen. So you can see your model. Now once this is done, let's use our knowledge of macros and create a point between these 2 points and also another point between these 2 points. Okay, so let's go to the macro option. So I want to define a macro along a vector. So the first starting point, I will select it as point C, and the second point is point E, which is this point, and I just want 1 point in between these 2, so I'll leave the number of points as 1 and I say create point. So you have a point 3 which is created between these 2 points and which is equidistant from these 2 points. Now similarly, I'll do the same thing and create a point between the point E and point F. So here I will change this to point E and this one to point F, and I say create point. So you got another point between these 2 points which is equidistant from point E and point F. Now I'll be creating 2 more bodies. So I'll go to the body option on the client specific toolbar. I'll create a body 0 and I say apply, and I create a body 1 and I say okay, so the two bodies, body 0 and body 1, they are created. And now I'll click on body 0 and I need to specify its properties. So mass, I'll be randomly giving it as 1 kg, and the inertia properties, just random values, just 4 ones. And let's go to the center of mass coordinate. So I'll put a check mark on this, use the center of mass coordinate system, and then here the origin point I will choose 0.3. So body 0 is created at this particular point. So now I will go click on body 1 and I'll specify the properties for body 1. So here again I'll give a random mass and random values for the inertia properties. And center of mass, put a check mark on this, and the point will be 0.4, just this point. So you created a point, you created a body at 0.3 and also at 0.4. Now let's go ahead and create geometries for the body. So right click on this particular icon on the client specific toolbar, which is the graphic icon, and by default it's a cylinder itself. So just say apply and again say OK. So you got two cylinders, but it is not shown on your graphical user interface because we need to specify the properties for these graphics. So click on cylinder 1 in the project browser, and then let's go to the connectivity tab. Here for the parent body, we'll be specifying it as body 0, which is this body, and origin for this body, for this particular cylinder will be the point C, which is nothing but this point, and the direction or the end point will be point E. So you got a cylinder. That's a pretty huge cylinder. So let's change its radius. So let's go to the properties and let's just give 1 mm as radius. Now let's go to the second graphic, which is the second cylinder, and do the same. Let's go to the connectivity tab first. So its parent body will be body 1, which is this particular body, and the cylinder starts from this point, which is point E, and it goes up till point F. And the properties, by default the radius of the cylinder that's created is 10, so we just want 1 mm radius for the cylinder. So now we have this particular model. So let's click on this, and this is basically the cylinder 0 that is already there. So we can now change the radius to 2, and let's continue doing the same for all the cylinders. Let's give the radius for all the cylinders as 2. Okay, so you have this now. So we've finished one particular stage in this model building process. So let's save the file. So file, save as, you want to save it as a model. So, and please try saving it in the same folder so that it's more convenient to find your models. So I'll be saving it as 4-bar bodies. So let me save it, 4-bar bodies, and I'm just giving it a suffix of class because I want to know that I've created it in this particular class. So, and then I'll just hit save. Okay, now it's time to create the joints. So we need to create 3 revolute joints. So for this, right click on the joint, okay, and change the joint type to revolute, and just click on apply twice. So this creates, if you can say OK. So now it's created the 3 joints that we want. Okay, so if you, by clicking apply, it won't close the dialog box. So that's the advantage. If you want to create 3 or 4 joints at a time, then you can just go on clicking apply instead of OK, so that it doesn't close the dialog box. Now click on joint 1. So this is joint 0, which is already created. Okay, and these joint 1, 2 and 3 are the joints that we created right now. So click on joint 1, go to the connectivity tab. Here, select free body for the body 1, and for body 2, select body 0. And you got to select point C for the origin. So a joint gets created at this particular point. So one thing that's remaining is its alignment. So we have aligned this particular joint, this particular revolute joint along the global Y axis. So let's do the same thing for even this revolute joint. So global Y, it gets aligned. Now we do the same thing to create 2 more joints at this location and this location. Okay, so we click on joint 2. So here in the connectivity tab, for the body 1, let's give it as body 0, and so that's this body, and body 2 will be body 1, that's this body. So a joint gets created between body 0 and body 1. So at this particular location is what we want, so that's point E. So the origin point is point E, and the alignment axis is the global Y. And say OK. So it's got created. Let's go to joint 3 now. Let's do the same. Body 1. Let's give it as body, select body 1 here for the body 1, and body 2 is the ground body because we need to create a joint at this location. So between, this is body 1 and the ground body, which is created by default. So we need to create a joint over here, and the origin is going to be point F, and we want it aligned to the global Y axis. Okay, so you can see the model that's created now with the 3 revolute joints, with the 4 revolute joints. Okay, so once the joints are created, now let's create a motion at joint 3. So at this particular location. So right click on the motion, let the names be default and say OK. So we want to create the motion on a joint. So at the location 3, so joint 3, select that. Now let's go to the properties tab, and we want to define the property by an expression. So click on the expression builder, and you can specify 1 times time, and the time, I mean the simulation time here. Okay, so then hit on OK. So we've defined a motion on this particular joint, which is the joint 3. Okay, now what we'll do is we'll check our model using the check model option in the tools menu. So if you do that, if you go to the degrees of freedom, we can see that, let me just bring it up again. Here we can see that the total number of degrees of freedom of this particular system is -3. So what does this indicate? The system is having some redundant constraints, right? So the negative value indicates this. So how did we get this -3? I will show you the calculation. So please concentrate on this particular slide in the presentation. So each revolute joint, right, it removes 5 degrees of freedom. And in the entire system, we have 4 revolute joints. So which makes it -5 multiplied by 4, which is -20. And we created one motion on joint 3, which removes 1 degree of freedom. So in total, the total number of degrees of freedom removed is basically minus 20 and minus 1, which is minus 21 degrees of freedom, right? And now we have a rigid body which is of 6 degrees of freedom, and we have a free body, body 0 and body 1, which means we have 3 rigid bodies. So that makes it 18 degrees of freedom. 3 into 6, 18 degrees of freedom. So now let's calculate the degree of freedom of the entire system. It is minus 21 plus 18. That will give you the negative 3 degrees of freedom. So that's what we saw here. Okay. We saw negative 3 for the entire degree of freedom of the system. Okay. So now let's run the model. So I'll be saving it as just 4 bar. Okay. Save, and I run the model. So once the model is run, I want to review the log file. Okay. So if you just go back and review your log file, it will show you this particular warning. Okay, the row deficiency detected. So it also gives you the warning, and it tells you that this may indicate a kinematic or over constraint model. Program will continue with redundant constraints removal. So MotionSolve takes a decision on removing some of the redundant constraints. So in that process, it might remove some of the joints, some of the constraints that are very necessary. Okay, so it gives you this particular warning in the message log. Okay, so now let's, out of curiosity, let's just go and animate the results to see what the animation looks like. Okay, so I'll slow down the animation. So this is the hyperview that it's opened, and now you can see the animation. Okay, so this is what it looks like. Now this may or may not be the right output that we want, because we haven't removed the redundant constraints. Alright, so now we go back to MotionView and try removing these redundant constraints. Okay, so in order to remove the over constraint, the middle revolute joints, what we have here, they can be replaced with the inline joint. Okay, so the ways how we can remove these redundant constraints, there's no single answer to it. There are multiple answers, and I'm just giving one answer here, and I want you guys to think about the other possibilities which are there to remove the redundant constraints in this particular system that we've created. Okay, so let's click on joint 2 here, which is this particular joint, and let's go to the drop down menu and select inline joint. Okay, so you can see that it's converted to a inline joint now. So now what happens is, the inline joint, basically it removes 2 translational degrees of freedom. Okay, so I'll show that to you in a presentation in a while. So how it removes the degrees of freedom and removes the redundancy. So I'll show you in a while how, by replacing this revolute joint with this particular inline joint, will help in removing the redundancy. Alright, so let's quickly check using the check model utility. You can see that the negative 3 degrees of freedom for the entire system is now gone, and it is 0. Okay, so this is now converted to a kinematic simulation. So how did we get that? Let's go back to calculations in the slide. So this is what happened in the background. So we have the 3 revolute joints now instead of 4 because we removed one of the revolute joints. So it is negative 5 into 3, which is minus 15 degrees of freedom. And we have one inline joint which will remove 2 degrees of freedom. And we still have that one motion which will remove 1 degree of freedom. So thus the total degrees of freedom removed will be negative 15, negative 2 and negative 1, which is negative 18 in total. And a rigid body will have 6 degrees of freedom, and there are 3 rigid bodies in the system. So 3 into 6 will give you 18 degrees of freedom. So negative 18 and positive 18 will give you 0 degrees of freedom, thus making it into a kinematic simulation. Okay. So let's go to this inline joint, and you can see that here the point is unresolved. So here I'll be changing it to axis, and it automatically takes it as the global y-axis since all the other joints are along the global y-axis. Okay. So now we know that the model is kinematic in nature. So let's now run the model. And yes, before running the model, let's create outputs because we want to measure outputs now. So let's go to the output option on your client specific toolbar. It is this option here. So right click on this. So it says output 1, say OK, accept the defaults. And now let's select expressions from the drop down menu. And in the F2 field, let's create the motion function to measure the force or the torque created by this particular motion. So go to the expression builder here. Okay. So it brings up this particular dialog box. Here you have multiple tabs open, so you need to go and click the force tab. In the force tab we have the motion option. So you need to select that. It automatically gives you the 4 arguments, right? So then you go to properties tab, back again, and you open you expand the motions folder, and then you expand the motion 1. In motion 1, you select its ID string. Okay, from the list of options, and then say add. So the ID string of the motion 1, which is created on the joint 3, it gets written here, and then I can just put 0, 7 and 0 for the rest of the arguments. So what does this indicate? If we go back to the presentation, so 0 here, it represents that the force or the moment will be reported at the I marker, and we put 7 here in the component. It basically returns the torque's Y component because we know all the joints that we have created are aligned about the global Y axis, and here also we have mentioned 0, so it is measured about the global reference frame. Okay. So we have this, say now evaluated to check if there are any errors in the expression that you've built. So if there are no errors, it doesn't give you any warning, so just say OK. So now this is done. So now let's run our model. So click on run and then click run option here, and MotionSolve now runs in the background and gives you the results. So the analysis is complete. So you can close this. Now what you want to do is, you've requested an output, so to see the plots you need to go to HyperGraph. So you can click on the plot option here. So this will invoke HyperGraph. Now you can click on this particular option, which is basically build plots. Now in the Y type you'll be selecting expressions because the output request what you've given is in the form of an expression. So you'll select this one and F2 as the Y component and click on apply. So this is what you see. So this basically gives you the torque that's generated by that particular motion. So here you have the time in the x-axis, which varies from 0 to 5 seconds, and in your y-axis you have the torque, and its units will be Newton mm. Okay, so you can now go back to your MotionView model and save it as 4-bar motion in the same folder. That's chapter 7 itself for your convenience. And this brings you to the end of the exercise 7. Thank you.